research in astrophysics and particle physics of the Master in Particle Physics and Physics of the Cosmos. As you know, this is a series of seminars that will take place during the course. It is for the students of the Master, but it's open to everyone at the Institute. So I just will recall how it works. During 1 hour we have the seminar. After that we will have some time for questions to the general public in the room. And after that we will ask everyone to leave, but the students, the lecturer, and any professor or teacher or lecturer of the Master that want to stay with us, just to have a discussion between the students and the expert. And I will leave Gervasio to present Juan Estrada, that he knows much better than me.
Okay, yeah. So we have Juan Estrada today with us. He actually came in a couple of days ago and gave a seminar yesterday about quantum sensors in high energy physics for the Institute. But since he was coming, we also thought it was a good idea to take advantage of his visit to give a seminar here for the master students and for everyone else. So today he's going to talk about the search for dark matter below the mass of the proton, below 1 GeV. He got his bachelor's degree in Balseiro, in Bariloche, in Argentina, and then he did his PhD in Rochester. And in Rochester, when he was doing the PhD in D0 at Fermilab is when we actually first met, several of us actually, with him, because we were in Fermilab during that period of our career. He did his PhD on essentially the mass of the dot quark, a very innovative method of extracting statistical information to do the analysis better. And then he worked on the central fiber tracker of D0. This is a tracker that consists of many scintillating fibers for tracking. After that, he worked on many things. It's too long, the list, and I will not go through everything, but in 2004 he got a Wilson Fellowship, which is very prestigious, and then he started since then to participate in the dark energy survey for the construction of a large CCD, large field CCDs. Since 2014, he leads the Dark Matter and New Initiatives Department in Fermilab. Since 2017, he works in the short baseline neutrino program. He's the manager of the neon detector installation. And since 2018, he's one of the experts at Fermilab for quantum science. And in fact, he's leading the project called a new single photon sensor for quantum imaging. He has won many awards and distinguishments. So I will not go through that list, but it's a pleasure for me to introduce Juan, who will talk about dark matter searches.
Thank you. Yes, so I will go over dark matter, especially the search for dark matter in low masses. So before I start the technical details of the search for dark matter, I want to give you an idea of why dark matter is so important for us and why it's such an exciting topic. Right? This is how our galaxy will look like if you are very far away, right? This is the sun here, this is the center of the galaxy, and the whole thing is spinning like crazy. The point is that we really are in something like this, right? Where we can, and all the galaxies look pretty much this way, where we are going around some center and have these strings from the gravitational force pulling us back towards the center, while there is this centrifugal force that is pushing us out. Okay? And the same is happening in all the galaxies. And then one trick that you can do is try to understand the balance between these two forces, right? What is pulling you towards the outside and what is pushing you towards the outside and what is pulling you towards the inside of this rotation. So that is done with galaxies not with our own galaxy, right? It's harder, but with the galaxies that we look from outside, and we try to understand these same kinematics of the rotation. Right? How each point here must have a balance between these two forces. So again, right, if you take any point, then you can measure the distance from one of these stars to the center of the galaxy, measure the rotation speed, and try to balance the force of gravity that depends on how much mass is inside, is towards the inside of the galaxy, and the rotation speed determines the force that is pulling you towards the outside. Right? Pretty much like in those games that I showed you before. So this has been done for many galaxies. This is a paper from 1980 that shows that is a summary of a lot of work that really at that point convinced many astrophysicists that there was something strange going on. Right? So this is the distance from the center of the galaxy. So each of these curves corresponds to a different galaxy. Right? Let's focus on the bottom ones. So this is in the y-axis is the velocity in kilometers per second, right? And in the x-axis is the distance to the center of the galaxy. And the point that I want to make is that this looks flat, right? As you move away, it looks flat. So, by the way, this work, the hero in this story, right, is Vera Rubin, that passed away a few years ago, and she was really pioneer on this research, right? So let's look a little bit about the math in this relation of balancing the two forces. So the gravitational force between two objects, right, is the mass of the two objects, the product of the masses divided by the square of the distance with some constant. Right? And then the centrifugal force is related to the velocity squared divided by the radius. So for something to rotate with a fixed radius, those two things have to balance, right? So for a velocity to be constant as a function of radius, then the mass, if you have, let's say this is the mass of the star and this is the mass of the galaxy, then the mass in the galaxy, the interior mass, right, has to be, over R has to be constant. So it has to be that the integrated mass, as you move to larger distance, has to be linear with R. But what is that we see, when you look at a galaxy, it doesn't look like that. Right? If you try to integrate all the things that are bright here, you get a curve that is like this thing. Right? So it doesn't look linear with R. So that's a problem, right? We see that the velocity distributions are flat. To make a flat velocity distribution, you need to have this relation. When we look at the luminosity, it doesn't look like that. So that's a big deal. The problem, was studied in a lot more detail than what I'm telling you, right? But I thought I'd try to show you mathematically the issue. But this is really a more modern way of plotting this, right? This is the velocity distribution and the radius, and then you have many ways of measuring the matter distribution there in a galaxy. So you can make this curve that goes to very high radius, right? And then, so the curve of expected velocity rotation from the visible disk is like that, right? This dash curve. And what you see when you measure the rotation, it looks very different, right? It's a big deal because it means that in most galaxies, the mass is not in the luminous part of the galaxy. So that's what motivates us to look for dark matter, this extra mass that has to be in the galaxies. Again, this really started to become mainstream in 1980s, thanks to the work of Vera Rubin, right? A lot of people were disappointed that she passed away before getting the Nobel Prize. So I guess we didn't find the dark matter fast enough. But anyway, so much earlier, there was, in the 30s, by looking at galaxy clusters, so the previous discussion was related to a single galaxy, and now looking at clusters of galaxies, and looking at the velocity distributions of clusters of galaxies, this guy, right, Zwicky, got convinced, so in case your German is not that good, right, so he got convinced that the mass had to be at least 400 times larger than those derived from observations of luminous matter. And if this turned out to be true, then we need dark matter. Right? He proposed this name for the first time. But the observation was not convincing enough to drive this, the community to really push for this. Right? Okay, so the story now is a lot more sophisticated than the rotation curves of galaxies, right? There are many ways to look for the gravitational effects of dark matter. One way that has been very successful is the search for gravitational lensing. What I'm showing here is an example, a real example of strong gravitational lensing. So you see there is a galaxy here, right? This orange dot, and then there was a galaxy on the back that was also another dot, right? But the gravitational field of this galaxy deformed the space around it so that what you see on the back becomes this arc. So that's an extreme case of gravitational lensing, but now we have built maps of big chunks of the sky with what is called weak gravitational lensing, which tells us is this same type of physics in a much lower field regime, which tells us where the dark matter is distributed in the universe. Right? So we know the dark matter. So the only point I'm trying to make is the rotation curves of galaxies were really what convinced everyone. But now we have a lot of tools to look for the gravitational effects of dark matter, and the picture makes sense from the gravitational point of view. Right? Every time we look, it seems like there is something else, there is dark matter, we just have to find it. There is this other example, right, the bullet cluster, in which two clusters of galaxies, that are more or less here, right? One another, one went through the other, and because of the because of the collisionless nature of the dark matter, the dark matter went through each other without any problem, and the baryons produced this shock wave, right? So in this case, we got this cluster of galaxies where we were able to separate the dark matter from the rest, right? And this is measured again with weak lensing, with gravitational lensing on these blue clouds, right? Unfortunately, the sky doesn't paint the dark matter one color, and so we had to do that painting ourselves. But the observations of the gas are done with X-rays, and these blue observations are maps of gravitational lensing. So again, right, the measurement starts with, everyone gets convinced with the rotation curves, but now we have a lot of other tools, a lot of other ways to look at the gravitational effects of dark matter, and seems really to be there, right? It's not an exotic thing that shows up in only one observation. Okay, so how does it look if we try to understand the total matter in the universe? Then we try to make an inventory of the total matter in the universe. We learned that about 85% of the total matter in the universe is this dark matter. So this is a very bad situation, right, for the particle physicists that are trying to find all the fundamental particles and fields, and we know that we understand only 50% of 15% of the total particles, right? So your friends that spend a lot of time at CERN are looking at this little part. But the situation is a little bit worse. Okay. I wanted to make another point. This is the other point that I wanted to make. The situation is even a little bit worse if you look at the whole energy in the universe, right? Not only the matter that works with the standard gravity, but try to balance the whole gravitational evolution of the universe. Then you find that, a big chunk of it is in the form of dark energy, which is a force driving the accelerated expansion of the universe. I'm not going to talk about that now, but that's another thing that we should be ashamed of, right? A big chunk of the total energy in the universe is in a force that we do not understand, and from the part that works with the standard gravity, most of the matter we don't understand either, right? There's a lot of work to do. So let's go back to dark matter and try to understand what tools we have to use to search for it, right? So instead of saying what dark matter could be, I'll start by saying what it cannot be, right? So it is not, this is what I have been telling you now, right? It is not in the form of stars and planets that we see. Observations show that there is far too little visible matter in the universe to make up this total energy that we are seeing. So it is not in the form of dark clouds of normal matter, because we'll see that normal matter interacting with radiation as it goes through, right? Like I showed you for that bullet cluster where we were seeing the radiation from the gas. It is not antimatter, because we do not see the unique gamma rays that are produced when antimatter annihilates with matter, right? So that's a way to look for this, is to to try to find these gamma rays, and we haven't been able to see them yet. We can rule out large galaxy-sized black holes. Imagine instead of being small particles, just big chunks, because we don't see enough of the lensing, micro-lensing effects in the sky to account for that. So we know it is cold. It was not relativistic at the time of structure formation. It's neutral because it doesn't produce light, right? And the interaction with the normal matter is very weak. So we have, right, a bunch of particles that form what we call the standard model. Most of the matter that we deal with every day is here, right? And all these particles, these particles here were discovered in different experiments, in cosmic rays and colliders and so on. But we know that the dark matter is none of these particles. So how much is there, right? So I try to put this number to give you an idea. So 1 proton mass every 3 cubic centimeters. That's how much we should see here, right, in this room. In our solar system, that's the density. So, 1 cubic centimeter is not that much, right? It should, if the dark matter has the mass of the proton, you should have about 3 particles there. So that's what doesn't seem that hard, right? We need to just build something that can detect those weakly interactive, slow-moving particles that are all around us. We don't have to go very far. So there are a few ways in which people have been trying to detect this dark matter. So if you think that we have the standard particles, the standard matter and dark matter, right? Then, and some way they can interact, where you start with 2 standard particles and you put them in a big collider with a lot of energy, right? You can produce dark matter. That's one way to look for it, right? To produce these particles by making 2 standard particles collide, right? They have some interaction that is going to be weak, and then you produce the dark matter. You can do the indirect detection, where the dark matter, 2 dark matter particles find each other and they annihilate, and then you see the normal particles that come out of that annihilation, right? So satellites, for example, looking at X-rays, cosmic ray experiments, are looking at these standard particles that result from the annihilation of dark matter. And then you can think about direct detection, which is the thing that I'm going to focus on, in which one standard particle and one dark matter particle interact in a way that they still give you a dark matter particle and the standard particle, and then you try to see how the standard particle changes, right? So you put a bunch of standard, a piece of material that you know about, and wait for a dark matter particle to hit it and produce a signal that you can then collect in your detector. So the industry for this is very big, right? It's I'm gonna focus on direct detection, and I'm gonna focus on one particular technology and try to go through the evolution of that technology. But this is, I'm gonna tell you about a small part of a huge field. So there are big detectors made with liquid scintillator of different kinds, looking at these dark matter particles. Usually what you have to do, if you think about trying to detect a particle that has a rare, a low cross-section, low interaction probability with a standard particle, then you have to go to a place where the rate of standard particles interacting with your detector is low. And one way to do that is to go underground. So this is just a simulation of a cosmic shower, right? I'll pick as an example. But you see that if you are in the surface, right, you will be affected by all this radiation, and you really have to go deep underground to get rid of all this radiation. Yeah? And then you put a detector deep underground that that is isolated from all that radiation and has a very high sensitivity, so that you can measure what happens to your detector when a dark matter particle hits it. Right? Unfortunately, we cannot make a detector with dark matter. Right? So we have to wait for this interaction of dark matter with standard matter, which is has very low probability, and that's why we tend to build big detectors with very high sensitivity and put them deep underground to isolate from the cosmic radiation. Okay, so now I'm going to go to a specific case of technology for dark matter detection. So the technology that I'm going to talk about is CCDs, right? And this is something that people in this institute are working on. So the idea is to use a CCD as a target for dark matter. A CCD is a chunk of silicon with pixels, right? And then the concept is very simple. A dark matter particle is a neutral particle that hits a silicon nucleus, produces the displacement of a silicon nucleus in your silicon crystal. That produces ionization, and you measure that ionization. Right? This is very much like the standard CCD cameras that are used commercially for imaging, right? And the silicon detectors that are used for particle trackers and so on, just promote a electron into the conduction band, and then you collect that charge, applying the right voltages in your detector. So I'm going to talk to you about a couple of experiments using this technology. One that I want to mention is DAMIC, which started operating many years ago now. In 2012, we installed the first version of this SNOWLAB, but in the last few years, it really has produced world-leading results, as I'm going to show you in a second. But this detector is 2 kilometers underground in a mine in Canada, and 2 kilometers of dirt over your detector is equivalent to 6,000 meters of water, right? So that's the technique that we use to go to a place where all the cosmic radiation disappears. So I'll show you, before going into more details of the hardware, I thought I'll show you some pictures, right, of how this is put together. So this is the first version of the DAMIC detector, and you can see that there is a little copper box here with a bunch of CCDs, and then we have a bucket of lead that isolates the detectors from the radiation that comes from the from the electronics here, right? So we put all this inside this vacuum vessel, right? And this is the size of the experiment, right? So we take all the parts, you can fit it in a truck and just drive, in our case, from Chicago to Canada, to Sudbury, where the mine is, right? And then you have to get ready to go 2,000 meters underground. And this is a working mine. So you have to take all the training to be a mine worker in Canada, which is a difficult career choice, I would say. But okay, once you do that, right, you get all the training, you put your detector in this little train that railroad car that goes into the mine, and you get down 2,000 meters underground, and then you have to walk 1 mile in these tunnels to get to your lab. Oh, by the way, because you have been walking on this dirt road, cave, right? Where there's water and things going on. You are all dirty when you get to the lab, so you have to take a shower, change all your clothes, use this community underwear, right? And then, but the lab is spectacular, right? The lab, so this team has, in this 2,000 meters underground, inside a working mine, built a really spectacular laboratory, where you have, once you are in there, is very cool place, right? You have all the things that you need to make a clean experiment, so you control the radiation from any piece of dust, and you have all the support of excellent engineers and so on. So this is what we build, right? It's we want to shield from, we are already shielded from the cosmic radiation, but every piece of rock here, right, has its own radiation. So we want to shield from that, and we do this by building next to our experiment that is in this copper box, a shield made of lead, made of copper, lead, and polyethylene, right? In different layers to stop charged particles and neutrons from coming into our detector. This is how the assembled experiment looks like, and this is one of our collaborators at Single-lepton. So after that, you make all this nice thing, and then you put a white box around it, so if you visit there, there's not much to see, right? Looks something like this. Now, since then, we have put a aluminum layer around it. So that's a boring thing about the dark matter experiments. When you go to one of these labs, we have many of them. What you see is just the outside shield, right? There's not much to see, but that's a good thing. Okay, so now let me go a little bit into the details of what this looks like. So we really need to do to be careful with the materials that we put out near our detector, and we really need to build a shield to isolate our detector from the environmental radiation. So we put this by having the detectors in this copper box, right? And then the copper box is inside a lead box built with ancient lead, that where all the radioactive isotopes characteristic of lead have decayed. So this lead is ancient and has been kept underground for a long time, so it has low radioactivity. And then you put another good lead around it, and then polyethylene, right? So it's building a shield for these systems is a critical part of the success, right? Because in the first iteration, we were completely dominated by the radiation of the environment. So with time, we learn how to do this correctly. So let's look at how the detector, the CCD, works. Now that you have gone underground, right?
20 minutos te alcanza. Con 20 minutos.
Sí. So you have gone underground, you build everything. Now let's look at how the detectors work. So the CCD, I told you, is a pixelated detector, and really those pixels are buckets of charge, where you collect the charge of each pixel, and then when you are done collecting the charge, you move it with some voltages in a very similar way to this bucket brigade, right? You move it along these lines, right, to a serial register, and then you drop it into one last bucket, which is the only one that you can measure. And then we make a very precise voltage measurement in this bucket, which allows us to see charge with a noise below 2 electrons. So that's a nice feature of the CCDs, right? Scientific CCDs are commonly operated with a readout noise below 2 electrons, which is a reason why they are still being used, right? This technology of moving the charge from one pixel to the other is not a fast technique to read out a silicon detector, but it's a very low noise technique for large pixels, so that's why this still has applications in science. For us, it means that we have a threshold of 7.2 electron volts, not 7.6. A noise of 7.6 electron volts. Okay, so scientific CCDs are used for astronomy all the time. This is how our dummy CCDs look like. So they are 4K by 4K, 16 megapixel CCDs with about 6 grams of active mass. So you may remember that I told you a few minutes ago that we needed large mass to look for dark matter, right? So one way to look for dark matter without a large mass is to set a very low threshold, because the probability of producing a signal in your detector goes up for lower signals. So we have an experiment with a relatively low mass, and it's made with these parts of silicon. Each one is 6 grams. Okay, so I will. So the silicon detectors are used as radiation sensors a lot, right? In particular, CCDs are used for X-ray detection. So you can see here how good a CCD is to measure the spectrum from X-ray sources, right? You can look at lines from aluminum, manganese, at different energies, and have a relatively good resolution, good linearity. This shows all the way from carbon, all the way from 0.3 kV to 60 kV. We can reconstruct all the peaks. So this is very commonly done with scientific CCDs. They are used for X-rays all the time, right? We are just taking the advantage of this very cool capability of CCDs for X-rays to calibrate our detectors in the search for dark matter. So this is at the surface. This is not underground. This is an exposure of, I'm showing here half of a CCD, right? And this is So it's 8 megapixels, and this is an exposure of 3 hours in the surface. This is what you will see if you put this detector in the surface. So they are really, we are constantly bombarded by a lot of radiation. It's amazing that we survive. But this is very low energy stuff. The point is that the detectors are very sensitive to radiation. So this is a good detector for this, right? And if you put it in the surface, you just get swamped with radiation. Right? Now, if you look at this picture, what I'm showing you is an image of several. So we have a box with CCDs like that in a stack, right? And I'm going to show you the stack going from the first CCD down. And you can see that you can reconstruct this beautiful mini shower, right, in the detector. So again, this is just to point out how cool these sensors are, right? Because they really allow you to see low energy things, and it has such a unique position resolution that you can reconstruct these little showers. Okay, so DAMIC is great, right? Our detectors are awesome, but we didn't find anything. But nobody found anything, right? We have all been looking for dark matter for many years. We did a lot of progress, right, as a community. And in this plot, I'm showing you a summary of those searches as of 2017, right? And if you are not used to seeing these plots, each of these curves determine the limit established by a given experiment or a proposed experiment for the search in dark matter, right? And they put a constraint in how what is the cross section of the dark matter. So if you think about dark matters as little spheres, right? This will tell you how large that sphere is, and this other axis tells you how heavy that sphere is, right? So in this corner, you are looking for very heavy particles that are very light, right? Like imagine a cloud in the sky, right? In this corner here, you are looking for very large particles that are also very heavy. So this is the easy thing to find, right? A big sphere that is very heavy, is easy to collide with. So all the experiments are excluding, all the part that is in green is excluded. That's easy to exclude. Here is the opposite, right? You are looking for tiny particles that are very light. That's very, very hard to see. So we are, working hard, right, to push this down, to push these to our light particles, and that's our job, right? So after getting terribly disappointed for 30 years of not finding anything in this area, we decided to extend our search going wider, right? Because even though there was good motivation to look for the dark matter of these masses, it was just a theoretical motivation, and we know often that the theories are wrong. So now we have extended the search into a much wider range of masses that go all the way from mini black holes into things that are very, very light. So I'm not going to cover the whole thing, right? Yesterday we were talking a little bit about axions. Today I'm going to talk about dark matter searches below the mass of the proton, right? So below below around here. Okay. So when the dark matter becomes light, your strategy to look for it has to be different, right? Because once the dark matter is much lower than the mass of the proton, then trying to look for the dark matter hitting a nucleus and producing as an observable signal is hard, because it's like throwing ping pong balls to a huge building, right? You will not move it much. So, with that, what you start doing is looking at the dark matter hitting not the nucleus anymore, but the electron. Right? So you look for, the electron is lighter, so you look for dark matter to hit an electron. You don't benefit from the fact that this thing is big, right? But it's the only way to look for the light dark matter. And there are many possibilities to look at electron recoil dark matter, and I will talk about one of them. Right? The one that I'm going to discuss in 10 minutes, right? is Skipper CCD. So I mentioned before how the CCD works. The Skipper CCD is the same, has the same basic functioning principle. Right? You move the charge from one bucket to the other, and then you take it to the sense node. The only thing that the only additional feature of the Skipper CCD is that you can actually measure this charge as many times as you want without destroying it, reducing your noise to as low as you would like. So you put the charge in the sense node, then you take it back, and so on, and you drop the noise to 0. So this is a little bit of the story, of the history of the Skipper CCD. The only thing I want to mention is that the Skipper CCD the design of the Skipper CCD has been around for a long time, right? If you look at old CCD books, they talk about the Skipper CCD, but they also hint that nobody will be as full as using it because it takes forever to read out. Right? But for us in dark matter, this is very important. Right? We want to go to a lower threshold, and we have the time to spend. So people kind of forgot about the Skipper CCD for a while, and we took it more recently and tried to push its performance to the ultimate limit. Again, this took a long effort, right? But now it works. So I want to show you this movie, which I really like, right? Which shows the way the Skipper CCD works. So this is real data. This is an image of a region of the CCD. This has 3.5 electrons of noise in a single readout. And I'm going to show you what happens when you read this multiple times. So this is the number of times you read, right? And this is how the image changes as you average all those samples. And you see that in the center of this image there is a single pixel with one electron. Right? That at the beginning was impossible to see, but now when you are get to a few thousand measurements, this is a very high signal to noise detection of that single electron. So then we have a tool, right? We look for the dark matter, we didn't find it, then we developed this new sensor that has a lower threshold and can look for electron recoil dark matter and can detect a single electron with very high significance. So we went from something like this that we use in the dynamic that is at Snow Lab right now, right, with 1.8 electrons of noise. This is a distribution of the charge on a pixel when there is no signal, to something like this where you can count electrons, 0, 1, 2, 3. So then what we want to do now is look for take our detector, right? The same way we did with dummy, put it inside a lead box, take it underground, and wait for a dark matter particle to hit an electron and promote one pixel from this beam to that beam. Right? Okay, the skippers are very cool, but they have the amazing feature of being allowing you to measure the exact number of electrons that you have even in a pixel, even when that number is a few thousand. Right? So this shows you the spectrum of the same way I was showing you the spectrum before for X-rays, and then I zoom here and you can see on this single electron count. Okay, so I told you about this before, right? We want to look for dark matter with these sensors, looking for electron recoil. So once you can count electrons, you can search for electron recoils, and this is the, for a dark matter particle of 10 mega electron volts. So we went lower now in masses compared to what I was telling you before. Right? This plot is for much lower masses. Then this is the rate that you expect as a function of the number of electrons, 1, 2, 3. Right? So you are looking for signals that produce a few electrons in your detector. Right? And with different versions, this is with 10 grams running for 1 month, right? This is with 10 grams running for 3 hours. You are already beating experiments that have much larger mass. And the reason for this is just your ability to see small signals. So this is our new choice now, right? Build larger and larger detectors with skipper CCDs that can look for this interaction, looking for the dark matter when the dark matter mass is much lower than the mass of the proton. So Sensei is this existing running experiment using this technology. This was installed now a couple of years ago, maybe last year, right? The installation, 2 years ago. Yes, at the Minos building. So because we are going to start with a small detector, we don't need to go such deep underground. We can survive with more radiation, so we start doing this at a shallow site, which is not a working mine, so we don't have to change our underwear every time we go there. But we started this operation in 2019. We already produced a couple of results, right? In 2019, we produced this limit of electron recoil dark matter search with skipper CCDs in a shallow underground site. And this is the type of distribution that we see, 0 and 1 electrons. This number is very interesting, right? We find 1 electron event rate at 3.5 10 to the minus 3 events per pixel per day. Right? So it means that if you are looking at 1 pixel, you have to wait a few thousand days, right? 3 years to see a single event. So this is quite an impressive performance for a detector, right? We want to do it much better. But this is already telling you that you need to wait. If you are 1 miserable pixel, then you will see something every 3 years. But this, with a very small detector mass and this shallow site, because of the very low threshold, it allows you to put a very competitive limit, right, in low mass dark matter search. That when we published, it was the most stringent limit for this type of dark matter. And again, this is the same, right? This is the cross-section for interaction with electrons, and this is the mass. The plots that I was showing you before started at around 1,000 MeV, right, 1 GeV. So this is much lower mass, and the new technology allows us to scan this space with less than 1 gram. We are already beating everyone else, except of course the people here at IFCA, sorry, that are also part of a standard CCD operation for this electron recall dark matter, in which we collaborate, and with the standard CCDs, larger mass, lower threshold, they are still able to push below what we did with Sensei, right? So we are beating each other all the time. Still, the plan is for all the CCDs dark matter searches to be done with skippers in the future, but this has the legacy of what we already have running at SNOWLab, and with a very, very sophisticated analysis, they are able to perform a measurement that is competitive with this new type of detector. So this is all very good news, right? It means we have the new technology, the standard CCD is also producing great results, and we are really starting to push for lower and lower masses. For low mass dark matter, we are planning experiments that will take this technology to its full potential. I show you the result of less than 1 gram. So the Sensei collaboration is planning a 100-gram experiment at SNOWLab. The LAMIC-M collaboration, right, with a big participation from IFCA, is putting together a 1 kilogram experiment in modal. And then we are starting the R&D for a 10 kilogram experiment, right, where Sensei and LAMIC start working together for building this challenging experiment. Right? So the future is all with skipper CCDs, and this is an awesome program that is just starting. After many years of development, we really are in the position to take full advantage of this technology. We are okay?
3 minutos.
Okay. So the skipper CCD is an amazing tool, and it's also a tool for other type of physics. I am very interested in using the skipper CCD for neutrinos as well. So in the case of neutrinos, you are looking for a very small signal produced by a recoil of the neutrino with the detector. So in this case, I'm showing you that, so 10 kilograms, we think we can build 10 kilograms in about 8 years from now. Right? We are talking about 20 kilogram experiment for neutrino. And they put it into a reactor and look for stereo neutrinos interaction. Right? It's a very nice tool because this interaction is independent of the flavor of neutrinos, so it's a nice way to do stereo neutrino interaction. But it's also a cool way to monitor a nuclear reactor. Right? The neutrinos come out of the core and all the shields of the reactor. So if you put, like in this case, a 10 kilogram silicon detector outside the nuclear reactor, 30 meters away from the nuclear reactor, then you can see the signals of the neutrinos, and you can know what's going on with the reactor. So it turns out that there is a lot of interest of being able to monitor nuclear reactors to understand what is the fuel cycle of the nuclear reactors. And of particular importance is to look at the very low energy neutrinos that come from the breeding blanket of nuclear reactors. And those can only be seen through coherent scattering. So this technology allows you to build a compact neutrino detector to look at this stuff. Right? So, but 10 kilograms is about 4,000 sensors, so it's hard, right? So we need to use the techniques that are used for CMS and big particle trackers. to put this stuff together, integrating a lot more electronics there. And in the last minute that I have, right, I want to tell you about the other thing that we are working on, which is with these same detectors, is to look at the dark matter decaying in space. Right? So a few years ago, there has been, so look at only this plot, right? The others are just different examples of this, but okay, so you cannot read anything, right? But what happens is that a few years ago, people looking at clusters of galaxies detected a signal of 3.5 keV X-rays that are not very easy to explain, given the lines that we know about, the atomic lines that we know about. So one possibility is that there is a 7 keV dark matter particle that decays into a neutrino and a gamma and an X-ray, and what we are seeing is that X-ray. Right? So this is what I'm showing you here is after putting many of these together. This is the spectrum, and this is about 3.5 keV, and there's a little band there. So there's a lot of observations of this. People have seen it in many places. Other people have looked for it and have not seen it. So our plan is to build this CubeSat, right? Put a bunch of skipper CCDs in there, no optics, and look for the signal of the dark matter decay in our own galaxy. Right? So if this is really dark matter and is decaying into this gamma, then one very nice way to do this is to go with a detector that has a very wide field of view, so it's not looking at sources anymore, like the X-ray telescopes that made the original observation, to look at the uniform production of this line in our own galaxy, and then integrating the sensor and see that. So it turns out that now it's cheap to go to space, right? So you can build something like that. Little kids at school are building these CubeSats that don't do anything, right? But they just take them to space. And so we have a design for a CubeSat that has a few CCDs. We have developed the electronics that fits in that form factor, and the plan is to have it in a couple of years in low Earth orbit, to put a little bit more garbage in space. But hopefully we'll answer the question, right, if this is really a signature of the dark matter using the same technology. Okay, I'll skip this. I'm done.